So today's webinar is on the characterization of photo curing polymers. My name is Keith Fonstock. I'm located up here in Burlington, Massachusetts, and this was put together with my colleague in Germany, Tobias Flock. So if you're familiar with NETZSCH thermal analysis, you may also be familiar with one of our other groups within our business unit, another business unit within our holding. You could also be familiar with pumps and systems, grinding, dispersing, or analyzing and testing, who I'm with here today. Here in analyzing and testing, we have a couple primary parts of our business. First and foremost, we create instrumentation. So that's thermal analysis for changes in dimension, mass, phase transitions, and enthalpies as a function of temperature, thermal conductivity, specific heat and thermal expansion, as well as calorimetry. But we have a secondary component of our business where we also do contract measurements, seminars, trainings, and webinars like this. But now that you have an idea of who we are, we can get on to the bulk of why you're here. So to start off, we all need to come from the same perspective. So we start at what is polymer curing? This is a process by which polymer chains are connected through linkages. This is typically cross-linking. And it can be promoted by chemical additives, heat, or electromagnetic radiation in the form of an E-beam or UV radiation, typically. Now, there's three standard types of UV curing. There's free radical and cationic, which are quite fast cures. And there's also dual cure systems where you use UV irradiation as well as heat to cause that cure to occur. There are different types of these ultraviolet adhesives as well. So there's constructive UV adhesives, laminating, pressure sensitive, and there's quite a few advantages to using UV curables as opposed to other types of curable materials. Primarily, they're high speed, high throughput systems, relatively low energy required, and there are no solvents in most of these systems. These go into all kinds of applications, anywhere from transportation, the aviation industry, to automotive, to marine, electronics, even dental fillers, and some in renewable energy. But what we're here today for is to figure out how we can analyze this actual process of using these UV curables as well as identifying parts of the cure. So to that end, we have these three products. There's the Photo-DSC, that's differential scanning calorimeter, which gives you caloric effects. So that's the amount of heat given off on one of these cures. There's the Photo-DEA, which gives you changes in dielectric properties, but more importantly gives you very accurate information about the end of cure, how long it takes to cure a particular product. And then there's the Photo-DMA, which gives you thermomechanical information about your coatings and your UV curables as they go through their process. But we'll start off by asking a couple questions. These are what most people come to us and ask when they say, I have a UV curable, I need to know, when does it start? When does this cure start? What wavelength of light do I need to use to cause this reaction to occur? How much heat does it take? What is the reactivity of this material? What's the glass transition after it's cured? All kinds of different questions that you can answer with these three techniques. So we'll start in with the DSC. This is a measurement of the energy difference between a sample and a reference material following a controlled program. That can be temperature or irradiation. And so what we see here is on the right, there's a sample inside an aluminum pan. On the left, there's an aluminum pan as a reference. As that material goes through a transition, that could be a cure, that could be a thermal transition like glass or melt, but it will either take in heat or give off additional heat as it goes through that reaction. That's what we measure with DSC. So what does that look like? This is the melting curve of indium itself, where you can see that there's a very clear onset. So that's when that's when this melt begins. So that's when the baseline changes and starts to go into this spike. But we can also get the peak area of this curve. That tells us how much heat is required to melt a material. Now, it doesn't have to only be the melt. We can also get a glass transition, which takes in some additional heat. We can get a cure, which gives off some heat, which is a little more important for these UV curables. But moving on from the design of a standard DSC, in order to integrate the photo portion of this Photo-DSC, we modified the lids of the DSC to accept a pair of light guides. This will split the incoming light into two segments, and it will irradiate both your reference side and your sample side. So the incoming heat that will occur, the heating that will occur from the irradiation will not affect the readings that we get. This way, the only heat we register is heat from reaction. So the DSC that we use for this photo curing is the DSC 204F1, and you can see our OmniCure light system to the left. On the note of light systems for UV curing, there's quite a few different choices. In the earlier days of UV curables, we typically used wide wavelength ranges for the lamps. We would use mercury lamps or some other types, but they cover a broad range. More recently, we've been switching over to more high efficiency, limited wavelength systems like diode lasers or high power LEDs. Now, these can be much more efficient both on power and heating, but they have to be optimized so that your initiators are active in that specific wavelength range. Whereas with the mercury lamps or the broad wavelength other lamps, you're able to have more wiggle room as far as the initiator wavelength. With this DSC, we can control the temperature, so anywhere from -100 to 200 C for the actual initiation by UV, and anywhere up to 700 C for the standard DSC testing afterward to get your additional heat cure or your glass transition or melt. But what always matters the most is the data that you get. So here we're looking at two different materials. Green is a good lot from a customer, and red is a bad lot. So each of these spikes is caused by an irradiation. So that pulse is 1 second at an intensity of 1 watt per centimeter squared in a nitrogen environment. So what we do is that 1 second pulse occurs, and you can see that each of these reactions is approximately a minute long. So there's a 1 second pulse, and then the material cures for approximately a minute. Just because it comes back to a flat baseline doesn't mean that it is completed curing. That means that that initiation has completed. So what we do is we have successive irradiations and see how much additional cure happens at each irradiation. That gives us control over that gives us a number for how much irradiation is necessary to cause complete cure, as well as the total amount of heat that is evolving from this material as it cures. And you can see that the amount of conversion that we get based on this heat evolved decreases with each successive pulse, all the way down to our 10th pulse, giving us nearly no additional curing. So first thing we do is figure out how much energy is required, energy input from irradiation is required to cause full cure. Second thing we can do is control the environment in which this reaction is occurring. So this is a single pulse for 3 different circumstances, all of them on the same material. This is pure nitrogen, nitrogen and oxygen split 50-50, and pure oxygen. And from the enthalpy of these cures, the amount of heat coming out, we can tell that in pure nitrogen, it's more than double the amount of curing that we get versus pure oxygen. Now, this can be very important because what this is doing is inhibiting the cross-linking reaction, and that heavily affects our final product as well as the amount of energy required to cure. So just based on those enthalpies, you can take the influence of oxygen content on the reaction of this HDDA. When I mentioned the different light sources, the big change these days is switching to more efficient systems because it takes a lot of energy and it introduces a lot of heat to use a mercury lamp. So the green curve on the top is from a mercury lamp irradiation, about 10 watts per centimeter squared. The red curve is from a laser, specifically at 447 nanometers. Now, with a suitable initiator that is active in the wavelength range of that laser, which this is, you can see that we actually get a greater curing enthalpy from an order of magnitude less energy. Now, we already knew what wavelength range to use for this initiator, but if you didn't know what sort of wavelength range wavelength range you need, you can use filters on a mercury lamp and sweep across different wavelength ranges to find exactly where you need to have your irradiation energy coming in. But all of these tests depend on a material which gives off heat during cure. Not all materials will, which is why we shift over to the DEA. This is the Dielectric Analyzer, and it measures changes in the dielectric properties of resins as a function of temperature, time, and frequency of an applied alternating electrical field. Now, all of these resins have ionically active compounds within them. So they'll have positive or negative charges on them. And with the DEA, we have electrodes and we will apply an oscillating field. So in a system where we would just apply a single field, negative charges would naturally move toward the positive electrode. Same goes the opposite way for the negative electrode. With an alternating field, we're able to move those ions back and forth. And with the DEA, we can measure the resistance to that movement. And that's where we get our ionic conductivity. Now, the way that this is typically presented on the DEA is the inverse of ionic conductivity, that ion viscosity. And there's a little bit of math behind this. If you would like to know more about this, we have a separate DEA presentation that can help you through that. But for now, what you need to know is that the ion viscosity is a really important characteristic that comes out of the DEA. So what does an ion viscosity curve look like for a curing material? That's what we're seeing right here. And there's 4 primary components that you want to look for. We have the minimum ion viscosity. That is the point at which ions can pass back and forth within your resin most easily. And that's the minimum in this curve right here. The second part is the slope of the upward trend in the ion viscosity. That is our reactive portion. That's how we can determine the reactivity of a particular solution. The third is the horizontal step. This is the difference between our minimum ion viscosity and the maximum where it starts to level off. And that fourth is the end of cure. So we determine that by an approximate horizontal level. That indicates that there is no additional curing going on. Now, this ion viscosity, the reason that it increases as we react is that it becomes more difficult for ions to pass from one side of the electrode to the other. And with more crosslinks, there's more resistance to that flow. So the DEA itself, you can connect this with a furnace. You can either put this into your own furnace, your own process, or you can use the DEA furnace that we have and connect that up to a UV lamp as well. Now, this furnace is quite nice because it has control all the way up to 400°C. It's very uniform, and you can control your environment around it. And you can see on the right what one of the sensors themselves look like. There's a series of comb electrodes along that sensor, and that's where we get our determinations. So for these specific UV curables, this is an electronic part assembly. So this is a coating for that, a fast bonding epoxy. And these are 2 different formulations, both about 200 microns thick. The irradiation is 20 seconds at intensity of 55 milliwatts per centimeter squared. Now, these numbers are what we've come up with, and for each process there will be different irradiation levels and irradiation times that are necessary, but you can figure that out through this process. But for this relatively idealized system, we were able to find that the 8640, the blue, hit its minimum ion viscosity at nearly the same time as the 8610. It gets to its reactivity component rather in a rather similar amount of time as the AD610. However, it levels off substantially lower than the 610, the red curve. Now, what do we take from this? So the reactivities are quite similar. The reaction times occur at similar periods of time after irradiation, but our level of cross-linking is different. We have about a threefold difference between our 610 and 640. We can also test based on different amounts of photo initiator. So here we're seeing in the blue curve a minimum amount of photo initiator, then increasing up to green, red, and black. And then each of the lines along the top, each of the arrows, indicates an additional irradiation. This is the same idea as on the DSC, where we had repeat irradiations to figure out how many irradiations and how much power does it take to cause full cure. So for blue, this occurs earlier than green, earlier than red, earlier than black. And it also gives us information about the level of cross-linking density for each of these. And if you want to do a dual cure, so if you remember early on, we had 3 types of UV curing, and the third was that dual cure. So in this case, this is where you put a part into an area that already has a UV resin dispersed on it. You then fix it in place with UV curing, then you heat it afterwards to finish the cure. So that's what we're looking at right here. This is only our UV curing component. So at about 2 minutes in, we have an irradiation. We can then see an ion viscosity as that green comes down to a minimum. Then we see our reactive component all the way out into a plateau. So this shows that our UV irradiation, that reaction has completed. And then following this red curve, which is our temperature, you can see that as it heats up, it begins to cure again. So we have an additional curing caused by the heating. Then as we cool back down to room temperature so that we can compare our before and after, you can see a substantial increase in the cross-linking density, or that ion viscosity. But this only gives us our ionic viscosity. It tells you a bit about our cross-link density, but much of the time you'll want to know a little bit more. You'll want to know how is this behaving mechanically as a result of this cure. And in order to get that information, we use the DMA. It's called Dynamic Mechanical Analysis, and it gives you thermomechanical data about a material based on a sinusoidal load as a function of temperature, time, or frequency. This is very similar to the DEA with one major difference. On the DEA, we have an alternating electrical field. On the DMA, we have an alternating mechanical load. So in order to understand the DMA, it requires just a little bit of background on mechanics. If you take a ball and drop it from 1 meter, it will bounce, but it won't reach all the way back up to 1 meter. It may get 3/4 of the way back. The energy that's returned after that bounce, that's called stored energy. This is an elastic reaction, so all the energy that goes in comes out. The difference in energy between where you dropped the ball and where it came back, that's our loss. So this is dissipated energy. On the DMA, we get both of these components. The way that we do it is we apply a stress, generally a rather small stress, and we get a small strain back out. The idea is that we're using small enough stresses and strains so that we're not permanently modifying this material. So we're able to continue testing this material without causing changes in the material just based on the mechanical oscillation. So we get through some mathematical miracles. Again, same idea here. We have a separate presentation specifically on DMA, but suffice to say that you can get a loss modulus, a storage modulus, and this tan delta. The tan delta represents a damping factor, energy dissipation. That storage modulus represents our stiffness. So that's what we're going to follow, because going forward, when you're designing a part, often what you really need to get is the stiffness parameter for that particular material. This DMA has a wide temperature range. You can use it all the way up to 600 degrees, wide frequency ranges, all these other things. But the big part here is that you can use UV irradiation on the compression sample holder. So the way that this works is you would spread a resin into that fused silica sample holder on the right. You then take a compression push rod, which comes into the top of that resin, and it will oscillate along the top of the system. You then irradiate from below and measure the mechanical properties at the top as they change with time. So the example that we have today is a dental composite. This is a UV cured dental composite. And what we were comparing for this person was resin A versus resin B. They were just two different initiator contents. So you can see we have consistent mechanical properties that we're showing stiffness here, E prime. We have consistent mechanical properties all the way up until that irradiation at about 3.5 minutes. Almost immediately, dental resin B started to react. It took about half a minute, nearly a minute, for the dental resin A to start to react, at least to be visible. You can also see that the end mechanical properties of these two materials were substantially different. This is a fairly similar set of information to what we got from the DEA, but it's in real mechanical terms that we can use externally and compare externally. So this has been a relatively quick run through of the different ways that you can analyze UV curables. Using the DSC, you're able to get enthalpies of curing reactions and degree of cure based on the heat output. On the DEA, you're able to sense all the way out to very end of cure using dielectric properties. And then the DMA, you're able to get mechanical properties of a resin or a composite all the way to the end of the cure. If you have additional questions about any of these techniques, we do have upcoming webinars on DSC and battery testing, but we also have a backlog of recorded webinars for all of these techniques. So I encourage all of you to go to the web address at the bottom here. So that's the end of it for me today. I will be staying around and taking questions. So at this point, if you have any additional questions, please just put them up into the chat box. And in a minute or two, I'll start going over those. So thank you for your attention. I hope you've learned a little bit more about how you can analyze your UV curables. Thank you.